Hi there. At this point, let's address a case, a typical simulation or directory organization. Okay, the input files. We're not going to run the cases. I'm going just to show you how to run the case. So here we already explored the source code. Now let's go into the example. So here you see that they are subdivided according to the physics. I'm going to focus in FLUBIO-PETSC, but the same instructions that are common can apply to all of the tutorials. So see here that we have the tutorials, the documentation PDF, so feel free to open there and you have the explanations. Certainly it can be improved, okay, and we are planning on adding much more tutorials, but now we have many tutorials there, so try to follow the instructions. So remember that FLUBIO doesn't have its own meshing utility, so all the meshes that are generated in another format, we are using OpenFOAM format. So first you will need to generate the mesh in OpenFOAM or convert it using OpenFOAM. Usually we get the meshes in FLUBIO format, converted to OpenFOAM, and then we pass it to FLUBIO. Okay, so you can put those meshes whatever you want. There is no limitation, but you need to know the location, because when we do the conversion, we need to point to that location. Also, your files, your cases, your simulations can be located wherever you want in your home, but try to keep everything organized. So as you go here, you see we have different cases. We'll open Laplace cavity and see here that this is a clean directory structure. Okay, so see here that we have 5 folders that are compulsory. You always need to have these folders. So what you do is just clone the directory and then you adapt it according to what you are doing to do. So this script will clean everything. So as you go into VC, it is intuitive, boundary conditions and initial conditions. So see that here in this case we're solving for the variable t's. You have p, u, you will have it. And as you open the files, you have for each of the boundary surfaces that you have, you need to assign boundary conditions. So we have the Dirichlet, Neumann, void is you don't want to solve in one dimension. So this case is one dimensional, and initial conditions. Okay, so see here that you call the Dirichlet like this. This is a non-uniform boundary condition, very easy to implement. Okay, so we're defining boundary conditions here. As you see, we're using JSON format. So if you don't know what is this format, just feel free to get familiar. Just go into the internet, search a little bit, but it's relatively easy. So remember, you have all the braces, commas, everything. So everything is based in this JSON format. Then you go into grid. This is the grid information. So here you don't need to do anything, just convert the mesh. I will show you that. But here you have all the information. Okay, so something important when you convert the mesh from OpenFOAM, you need to have the decomposition even if you are running in serial. So you need to have one processor. Okay, so be careful on that. We're going to work those skills during the tutorial. Then you go physical properties, if there are. So for this specific solver, we have these two. If you want to know what properties you have, just go and read the source code. But in the tutorials that we're giving you, we're exposing the basic actions. Then we go post-processing. Okay, so here after we run, we're going to get the fields, everything. So for the moment we don't have anything. Monitors, here we have residual forces, and this is the VTK to open with Paraview. Later I will show you that this will get populated when we run. And settings, here we set all the settings. We control the simulation. So we have these 4 input files. You open again, see that it's JSON format. So see controls. Okay, so you have runtime parameters, maximum time, iteration, safe grading, stuff like that. Linear solver. So this directly point to PETSC. So here you can access all those options. Okay, then actions. Okay, so here you have this basic discretization. Okay, so see that grading, greenhouse, diffusion, tear, everything. So tear by tear, you can control that. And if you are running a steady state, here is where you set up. Okay, so on the relaxation. So these are the basic solvers, okay, that you will find in every single tutorial case. But according to what you want to do, you will have different actions. So what I want to show you now, just let me open here. Then I have some basic instruction here. So let me run this case. Okay, so see here that I open a terminal. I already sourced Fluvio. So you see that the first step is converting the mesh. So this is the script that that comes with Fluvio to convert the mesh. Remember, it's very important to know the location of the open phone mesh. Okay, so see here that given the relative path, you can give absolute path. So go here, then you have it here, and you have your mesh here. So important that this case is serial. Even if it's serial, you need to have this decomposition, okay? So let me go here, I go back, I run here, and it will do the conversion, okay? Also something important as well, that to run this, you need to do it inside the directory grid. So you go inside there and run this one, and it will copy all the mesh information. So see, it's written, everything you get this meshes has been converted. Now it's in Fluvio format, that is a binary format. And now we can run the solver. So to run the solver, you can type FLUBIO-PETSC, okay? You can use the redirector as well, there is no problem. And you can put this one also if you want to run in serial. You don't need it in serial, but if you want, you can put it, okay? So you're running in parallel, we're going to show you in a tutorial. So in this case, it's serial. And it's running. You have the solution, you have here your output, you see residuals, everything. And now as you go here, in see monitors, here you have all the residuals. You go into fields. Now here you save the fields in binary format. You have gradient and everything. Okay. And here we should have the BTK. We don't have it because we need to convert this format into this one. So we use this utility. Put that like this. Later we explain you in the tutorials what to do. And you go here and you have the tutorials, the fields. So now you open ParaView. And you can post-process that data. Go here, open, and voila, you have your solution, okay? So this is just to show you the organization, how all this file, where are the files located and what to do. So here you see that you have your residuals, your arrive convergence, everything. So this is the case structure. So remember, what you need to do is just clone one of these cases and then adapt it according to the physics. So we're giving you a few tutorials here, a few sample cases that you can just use it and then clone it, and then you adapt it. What you need to change is just the mesh and the name of the boundary conditions. Okay, so that's all for this case. At this point, we're ready to start to run a few tutorials. So thank you for your attention, and I hope you are enjoying Fluvio. Bye.